How you doing? I'm Mr. Rose, and today we're going to be getting into some dynamics, specifically Newton's laws. So first I want to talk about what I have drawn here. It's a very concrete problem, and this is going to be a problem that we're not actually going to go through and solve entirely. We're going to get some very powerful observations out of this, however. What we're going to look at is this mass, which I have on a plane, attached to a spring, and it's going to be pulled with some force that I call Fa. Now this K is what's called the spring constant, or the thing that might be holding or pushing or pulling that mass. So very simple put, I want to know what is the force acting on this mass. Now, first of all, it's a very good problem because it's a representative problem. Here in physics, we want to look at a situation and be able to predict what happens later and later and later based on some parameters. This is a very simple situation, but we can replace it with more complex situations. We can replace the mass with, say, the Earth. We can replace the spring with, say, the sun and the Earth going around the sun, for example. So there are lots of differences that we can put into these situations that are all applying the same principles. And those principles are Newton's second law. So you see this, and I ask, if I pull this mass, what is the force acting on that mass? You might be getting very excited right now and say, oh, I can do that. I know Newton's second law. Newton's second law is simply F equals ma. But there's a catch, something that people may not have told you before. Ma is not a force. What do you mean ma is not a force? We plug it in. Ma, or the mass times the acceleration, is actually a response to that force, to that pull of this object. So what we need to do now, in a little bit of a more advanced course, is we need to notice, like you've noticed before without ever really thinking about it, that there are, in fact, two sides to this equation. There's the F side, looking for the force side, and there's my mass times the acceleration side. Now I'm going to offer you this right now with no proof, that the force, or this spring's force, is equal to negative K, that is this constant for the spring, times X. So now you report that to some people that are going to examine spring physics. They're going to be able to examine that and tell you exactly what it is. This would be a very simple equation to prove just with our basic knowledge right now. For example, at equilibrium. What is equilibrium? Equilibrium is if nothing's happening. So if there was nothing acting on this object, say right there, which I could call x equals 0, well, whatever that spring constant is, if it's at 0 where it's not getting pushed or pulled at all, it's just nice and relaxed, 0 times k is 0. Looking at what we previously always knew on the right side of the equation, if this side is 0, the mass can't be 0, thus the acceleration must be 0. So there's no force acting on that object. So it's very easily proved with that simple case that I can say that the response of this, if it's at x equals 0, is 0. Well, now I want to look at the right side of this equation. The right side of this equation is what we've always known before, mass times acceleration. Right underneath it, you can see I wrote this a little bit more complicated, because something that we know about acceleration at this point in time is acceleration is two derivatives away from acceleration. In other words, I have a second order derivative. This d squared x over dt squared is saying I'm taking the derivative twice of my position to get acceleration. Those two things are one and the same. Acceleration is just two derivatives away from position. Why am I even pointing this out? Why is this helpful to us? Well, Newton's law is just a law. It's like a postulate, something we can't really prove. But if I write out this expression now, my left side, which I gave you as my force, my right side, which is mass, times a second order differential equation, d squared x over dt squared, I get this mathematical expression that I would then be able to solve. So I know this looks kind of difficult to solve, so I'm going to take it a step back. If I got rid of this, if I just gave you this second order derivative, even though we might not be comfortable with derivatives left yet, if I said mass times d squared x over dt squared equals some constant, 50, eventually you're going to be able to look at that and say, you know what, I know how to solve for that. Bring that m over there, so I'd have 50 divided by m, and now I'm looking for something where two derivatives later, I have an answer. So basically, I would have like a t squared times some number is equal to 50m. It'd be something that I can easily solve. But this expression isn't that easy. This expression, or my x position, is actually a function of time as well. So here, I have my final second order differential equation, something that's very difficult, with two distinct sides, something on my left side and something on my right side. Now, this expression, or a second order differential equation, is really just an unknown function in terms of its derivatives. That's all it is. How do we solve for second order differential equations? Well, there are a couple of ways to do it. Number one, we can go ask some math folk, because they like to do work for us physics folk. Not necessarily suggested. Number two is you pull out your handy dandy table of integrals. Everybody's got a table of integrals. You should always carry a table of integrals, aka the internet. You can look them up if you know what you're looking for. The third way is really to guess. And as foolish as that sounds, that's actually how we solve second order differential equations. We guess an expression that fits. Now we're going to get to that way later in the year, but for this simple example of this spring oscillating back and forth because of this mass, you actually already have a good idea of what this solution for a second order differential equation is. If I pull that spring and I asked what physically it would look like, say on a position versus time graph, we would get this nice curve, a nice sine or cosine curve. That sine or cosine curve is actually one of the accepted solutions for a second order differential equation. In other words, if I take not one but two derivatives of, say, cosine, I get back a negative cosine, and that will come again later on in the year. The other reason why we're looking at this simple expression, which cuts to be very complex very quickly, is to exploit some more things that we see out of this. In other words, as this oscillates back and forth, I have my nice graph here, and hopefully you can see this back and forth motion, this repetitive harmonic motion would look like that nice cosine curve. Is that going to happen forever and ever and ever? Obviously, the answer to that is going to be no. Why is this not just going to oscillate back and forth forever? All of you know right now, you're thinking, obviously, Mr. Rose, it's not going to do that because of friction. Well, friction is a special force. And we're going to talk about some special forces also today. Not every special force there is, but a lot of them that we're going to be speaking about throughout this course, at least early on. In no particular order, I have special forces of a gravitational force, I have a weight, I have a normal force, I have a tension force, and I have a frictional force. Now, I would like you to take some notes on these forces. I'm going to highlight some very important things. First, gravitational force. Now, one thing I'm going to read to you is the gravitational force is a force on a body that is a certain type of pull towards a second body. So here I have my Earth, and we know the gravitational force for all of these people are pointing to the all pointing to the center of the Earth. Now, in our case, the Earth is that second body. It doesn't always have to be that second body. In reality, those two people spread so far away have a gravitational force pulling them together. We just tend to ignore it. So right now, we're talking about a force on a body that is a certain pull towards any other second body. We just usually take that as the Earth. Now, something that you may or may not be aware of, weight is not a force due to gravity. Very importantly, not a force due to gravity. What weight actually is the magnitude of the net force required to prevent a body from falling freely, say, to the Earth. In other words, I'm holding this marker way up in my hand because I am providing some force that is keeping it from falling down. That is how we measure weight, and weight is measured with a balance here on Earth, not a scale. That's something that is just kind of a small detail. What else do we have? We have a normal force. By definition, the normal force is a supportive force that is always perpendicular to a surface that it's standing on. So right now I'm standing on the ground, I'm depressing the ground is pushing up on me underneath my feet, and this is a direct application of Newton's third law. Next we have tension. Tension is always typically in a cord, in a chain, in a rope. One thing about tension is often in the cord, the rope, the chain is magic, and by magic I mean we often say that they're massless. If it is not massless, it will say that in the problem, that our rope is not massless. But if I take my rope and I pull it around something and I pull it taut, a fun physics word, then that tension is directed away from my body along the cord in the direction that it's being pulled. Or in the opposite direction. I'm lying. In the direction that it's being pulled. I apologize. That tension force is always directed away from the body. So if I have something hanging tied to a rope, the tension is pulling up. If I'm pulling it towards me, the body over there, the tension is along the rope towards me. That's what I was trying to say originally. Friction. Friction is something we've talked about a lot, but a lot of people don't actually know what friction is. Friction is actually bonding between two surfaces. One surface on top of another surface as it is either being pulled or attempted to being pulled, attempted to be moved. Friction is always parallel to the surface that it's moving against or attempting to be moved against. There are two types, actually there are more than that. There are two types of friction we study a lot, which is kinetic or moving friction and static, stationary friction. In addition to that, we have fluid friction and rolling friction, both of which we're going to talk about. Friction is a retarding force, in other words, it slows motion down. And friction is always, always, always opposite the direction of motion. Just got to move up to the front of the room. And through the magic of terrible editing, we're now at my second board. One thing I forgot to mention about friction, often we say friction is negligible. Again, if we need to account for friction, it'll be stated in a problem. But we always start with the simplest solution, or simplest, not solution, orientation. Frictionless pulleys, massless ropes, frictionless tables until we get a little bit further in our course. Now that we know a bunch of these forces, what do we need to do with them? Well, we're going to use them to, again, predict things that are going to happen. That's what we're doing when we study physics. In order to do that, we're going to do two things. First, we want to identify any forces acting on our object. In other words, we're studying that mass of a spring going back and forth. We need to identify every actual force that's on there. Second, we need to be able to draw free body diagrams. So here are just some quick notes on how to do those things. First, to identify forces. What you want to do is you want to identify what a system is and what the environment is. Now, the system is the object that we're looking at. The environment is really everything else, anything the environment touches. So what we want to do is we want to sketch out a situation. That situation has an object, a system, and then anything that touches it. We want to draw a closed surface around our system. In other words, draw something around the object you're studying. Next, every point on the boundary of the curve that touches that system is where our environment exerts a contact force. If I am standing on the ground, there's a contact force between me and the ground. We want to name and label all of our contact forces. Make sure that there's at least one contact force. Sometimes there are more than one, but at least one contact force everywhere that happens. And last, name and label any long-range forces. What's a long-range force? That might be a force that is not in that contact position. The only one we know thus far that we'll be talking about is the force due to gravity. Once we know all of that information, we're ready to draw our free body diagram. Free body diagrams are the key to solving almost every Newton's laws problem. Free body diagrams start very simple and get very complex. So, what you want to do with the free body diagrams? ID every real force on the object. As I'll mention in the future, free body diagrams have only real forces on them. Second thing we need to do is we need to draw a coordinate system. I want to know what direction is positive, what direction is negative. So here, this would be my positive x and my positive y. Sometimes there's a z direction. If I have something on an angle, I'm going to choose a coordinate system that's also on an angle. Next, I'm not going to go on to this complex sketch that I have. I'm going to represent my object with either a dot or a box. That could be anything I want. Draw vectors to represent all of our identifiable real forces. Draw and label. Skipping ahead. Once I do that, this part is really just my check. Not actually necessary, not necessarily on the free body diagram. But if I can tell, I want to draw and label the direction of my F net, of my net force. This does two things. One thing it does is it tells me if F net is going to agree with my acceleration. Those two things are always in the same direction. Doesn't matter if it's positive or negative, speeding up, slowing down, going in a circle. F net has to go in the same direction as the acceleration. Also, if F net is 0, like we saw earlier, say if there was something in equilibrium, if the net force is 0, there's no acceleration. That should make things a little bit easier. Now notice I said do not put this on a particle because it's not actually part of your free body diagram. That's just to help us solve things. That's all I have for you today. We'll get into some deep examples in class. Like always, if you're on the YouTube channel, please feel free to like, click, and subscribe. If you have any questions, by all means, drop me an email. I'll see you in class. Thanks a lot.